The gentleman that I'm about to introduce is Dr. Peter Lindemann. How many of you have heard of Peter before? All right. Peter is somebody that I go to for what I would call wise, sage advice. He's someone that knows how to not get pulled from a direction from an emotional standpoint or hype. And he is the person that I go to quite often as it especially relates to this field. And time again, you know someone's advice based on how well it works. And Peter's always given tremendous advice. So I consider him a wise sage. And he's done some advisement for New Energy Movement and also for the Nui Foundation. And he's just an amazing individual, friend. So he spent 46 years studying how to tap into energy sources that are freely available. That's a long time. And you can see where that wisdom, has nurtured and come from. He's an inventor, researcher, historian, author, lecturer, educator, and also a longtime meditator. And why is that important? Yeah, well, research studies show that the long-term meditators have a capacity to keep, a neutral mind and be in an alpha brainwave state, which allows you to see more information versus limited information, and doesn't allow us to get the what we call the amygdala hijacked and, respond to things in a very reactionary way. So that's important in this field. And my guess is Peter has seen more than I can possibly even understand at this point. In 2000, he started an organization called ClearTech, and he's produced an extensive amount of online material. And besides his free education website, some of the publications include The Free Energy Secrets of Cold Electricity, Tesla's Radiant Energy in 2006, Electric Motor Secrets in 2007, Perpetual Motion Reality in 2012. So it is my absolute pleasure to introduce a wonderful human being and a wonderful individual in this field that's participated in a lot of material that many of you have read, Dr. Peter Lindemann.
Is this mic on? Can everybody hear me? This is good? Okay. Thank you, Susan, for that inspiring introduction. I wonder who that guy is. But hopefully you won't be disappointed at the end of the day. So thank you also the whole Global Breakthrough Energy Movement staff. They're all in the back. They're doing an impossible job. And all the volunteers that help them. Thank you for attending here today in the conference room, and also all of you at home live streaming. Thank you for participating. Your support over the years has helped build the conversation about advanced alternative energy solutions, and hopefully is hastening the day when the best of these technologies breaks through the institutional resistances that have held it at bay for so long. It is my honor today to address you and speak to you on the topic of Thank you, Susan, for that very gracious introduction. Thank you also to the whole Global Breakthrough Energy Movement staff and to all the volunteers who make this event happen. And finally, thank you all for attending this event, both here in the conference center and at home by live streaming. Your support over the years has helped build the conversation about advanced alternative energy solutions and hastened the day when the best of these technologies breaks through the institutional resistances that have held it at bay for so long. It is an honor for me to address you today on the topic of the science behind Tesla's self-acting engine. Nikola Tesla was one of the last and greatest of the dying breed of natural philosophers coming out of the 1800s. In that era, inventors were trying to determine what nature was doing so they could imitate it. Beyond this, natural philosophers were also trying to discover why nature behaved that way. 120 years ago, Tesla was best known for developing the system of alternating current electricity that was coming into general use. They openly called him the man who invented the 20th century. By the 1960s, he had been completely erased from the history books. Today, Nikola Tesla is best known for his Tesla coil and his boundary layer turbine. In my presentation today, I would like to discuss with you Tesla's profound interest in tapping solar energy. In June of 1900, Tesla published a 30-page article in Century Illustrated magazine titled "The Problem of Increasing Human Energy, with special reference to the harnessing of the sun's energy." This image is the first page of the article as it originally appeared. In this article, after discussing every known source and method for harnessing energy for society, he starts proposing new and radical methods for future development. The method he gives the most attention to is what he calls his self-acting engine. The machine, as proposed, was designed to extract degraded solar energy in the form of heat from the ambient air and drop it into an artificially maintained cold spot so as to produce mechanical energy from the heat extracted. He referred to this as the ideal way of obtaining motive power. He openly stated that the amount of energy available in the heat of the ambient air was greater than all the coal, all the oil, and all the waterfalls in the world. And because this heat was constantly being replaced by the sun, he believed it was inexhaustible and the ideal way to harness solar energy and power civilization. Since its original appearance as an article in a larger publication, this extended essay has been reprinted as a standalone booklet dozens of times. In spite of this, I have never heard of any inventor seriously trying to follow up on Tesla's ideas. The self-acting engine, or ambient air heat engine as I like to call it, remains out of the conversation about viable alternatives to coal, oil, natural gas, nuclear, and hydropower. There are a number of reasons for this, but for the most part, the arguments focus on the generally low efficiency of heat engines and the diffuse nature of the heat resource in the atmosphere. To begin this exploration, I'd like to share with you a number of quotes from this article so you can get the flavor of Tesla's ideas and approach. I was vainly endeavoring to form an idea of how to utilize more of the heat energy of the medium when I read some statements from Carnot and Lord Kelvin, which meant virtually that it is impossible for an inanimate mechanism or self-acting machine to cool a portion of the medium below the temperature of the surrounding and operate by the heat extracted. These statements interested me intensely. Evidently, a living being could do this very thing, and since the experiences of my early life convinced me that a living being is only an automaton, or otherwise stated, a self-acting engine, I came to the conclusion that it was possible to construct a machine which would do the same. Suppose that an extremely low temperature could be maintained by some process in a given space. The surrounding medium would then be compelled to give off heat, which could be converted into mechanical or other form of energy and utilized. By realizing such a plan, we should be enabled to get at any point on the globe a continuous supply of energy, day and night. A closer investigation of the principles involved and calculation now showed that the result I aimed at could not be reached in a practical manner by ordinary machinery, as I had in the beginning expected. This led me, as a next step, to the study of a type of engine generally designated as turbine, which at first seemed to offer better chances for a realization of the idea. My conclusions showed that if an engine of a peculiar kind could be brought to a high degree of perfection, the plan I had conceived was realizable, and I resolved to proceed with the development of such an engine, the primary objective of which was to secure the greatest economy of translation of heat into mechanical energy. In early 1895, Dr. Carl Lind announced the liquefaction of air by a self-cooling process, demonstrating that it was practicable to proceed with the cooling until liquefaction of air took place. This was the only experimental proof which I was still wanting, that energy was obtainable from the medium in a manner contemplated by me. So, what did Tesla find? Carl Lind's work with the liquefaction of air forced him to go back and study all of Boyle's gas laws and the mathematical equations that accompany them. He found that when Joule had calculated the heat work equivalent of a compressed gas, he looked only at the mechanical work and the rise in temperature, and he neglected to account for the simultaneous rise in the pressure of the gas. This oversight had been ignored since 1845, and I might add, seems to be ignored right up to this day. He was sure that correcting this oversight would allow him to accomplish his goal. Gas laws state that the temperature and the pressure of a gas are directly related, but this does not necessarily mean that as the pressure rises, there is more heat present. When a gas is compressed, it already has a specific heat content, which now must exist in a smaller volume of space. This heat densification is more likely the reason we see a temperature rise. The mechanical energy used to pressurize the gas becomes the higher pressure in the gas. Therefore, no energy is converted to a different form, and no new heat is produced other than by friction. Arguments like this were originally brought up against James Joule's postulates, but Tesla rediscovered this error and believed it provided him the way to make his self-acting engine work. So let's summarize Tesla's ideas. This is fairly simple. 1, he needed to be able to establish and maintain an artificial cold spot so that heat from the ambient air could be absorbed by it continuously. 2nd, he needed an engine of extremely high efficiency and unusual design to convert the heat of the ambient air into mechanical energy, leaving cold air as a byproduct. Proof that he was working on these ideas is found in the patent record. One of the contributing inventions Tesla developed in his quest to solve the self-acting engine was his now famous boundary layer turbine. This is a little-known fact of history most people are not aware of. The reason why he developed the turbine was bound up in his attempt to prove out the self-acting engine. As I quoted earlier, Tesla admits he had considered a turbine type of engine as a possible solution. When the turbine proved to be insufficient, he moved on to produce his mechanical oscillators, which he eventually believed held more promise. And finally, this patent from 1901, titled Means for Increasing the Intensity of Electrical Oscillations, where Tesla shows a secondary coil immersed in a pool of liquid air, where the electrical resistance of the coil is reduced to extremely low values. It demonstrates that he was indeed following up on Carl Lind's work with the liquefaction of air and whatever else he could discover about its properties. Tesla did not claim that his supercooled coil lost all of its resistance. and therefore it was Dutch physicist Hugo Onnes who is credited with the discovery of superconductivity in 1911, 10 years later. And finally, this quote, Tesla summarizes his efforts as of the time the article was published. Much of this task on which I have labored so long remains to be done. A number of mechanical details are still to be perfected and some difficulties of a different nature to be mastered, and I cannot hope to produce a self-acting machine deriving energy from the ambient medium for a long time yet, even if all my expectations should be materialized. So where does this leave us? Tesla never finished his work on the invention and never built a working model. It was obvious he was working on it. In fact, in all of his major publications after 1900, he never mentions it again. So the question arises, is looking deeper into this a fool's errand that thermodynamics assumes is impossible? Or is this simply the greatest overlooked invention of the last 120 years? So let's look at what technologies have been developed since the year 1900 and see if any of them can help us finish the work on this. There are dozens of films on the internet showing people running a low-temperature Stirling engine on the temperature difference between the ambient air and some dry ice. I've got one of these little things that runs great on dry ice. While a few pieces of dry ice do not represent an inexhaustible cold spot, it does represent at least the beginning of the idea that a heat engine can be run from the heat in the ambient air if there is a cold zone to drop the heat into. So this is the first step. Does a heat engine work in this temperature gradient? Yes, it will. Heat engine number 2. The drinking bird was first developed in China as a children's toy in 1910. But does it fulfill Tesla's vision of an atmospheric heat engine that produces mechanical energy by absorbing ambient heat and then dissipating it back into an artificially maintained cold spot? It can, but for the most time it doesn't. If the water temperature is cooler than the air temperature, then the machine operates like a low-temperature Stirling engine, moving heat from the ambient air into the water while the bird bobs for a drink. But if the water temperature and the air temperature are the same, then it will only work if there's low humidity, so that the cooling effect is produced by the water evaporating from the felt-covered head of the bird. But it is a fun fact to see that the drinking bird can violate Lord Kelvin's statement where he said, "It is impossible, by means of an inanimate material agency, to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of its surroundings." The drinking bird violates that. Now, even so, having a 20-meter drinking bird in your backyard is not what we're going to be talking about today, okay? So, we must solve a few issues. The first problem is, how do we produce and maintain an artificial cold spot? Tesla never really figured that out exactly. And second, how do we create a heat engine of very high efficiency? For the solution for problem 1, I'm going to focus today's lecture on the use of what I call an advanced heat pump. And the solution for the high efficiency heat engine, I'm going to focus on an advanced type of Stirling engine. Now both of these types of machines came out of the early 1800s. So this isn't all the science on these devices is known. So please bear with me on this, especially if you consider that these are very poor choices to explore. So this is the way a modern heat pump works. We can see the heat comes into here. It causes the mixture of liquid and gas material to be fully vaporized so that this comes out of the cold vapor. Then this is compressed and it raises the temperature or densifies the heat in it already. Here, the excess heat this is higher than the ambient, so the excess heat leaves the system here. That cools it off, and then the rest of the pressure is released here at the expansion valve, at which point some of it vaporizes and some of it liquefies, and then it comes back down and the cycle is returned. So this is this is the idea of a heat pump, okay? The idea that artificial cooling effects could be accomplished by a vapor compression and decompression cycle was first proposed by Oliver Evans in 1805. The first working model of such a device was patented in 1834 by Jacob Perkins. Over the next 80 years, dozens of other inventors contributed to the development of this process. It seems obvious that Tesla should have known about these developments, and therefore it is also logical to assume that he did not consider this path of exploration valuable, or he would have mentioned it. So again, it's probable that Tesla was unaware of the modern concept of the coefficient of performance, whereby a heat pump can contribute or combine an environmental input with a conventional input to produce energy effects in excess of the conventional inputs. So the big breakthrough comes in 1930. How many of you have seen and read the patent of John Huston? Okay, this is a patent that issued in 1930 in the US patent system. It consists of an electric motor that drives an air compressor. The heat made available from the temperature rise is removed and used for heating a building. The pressure left in the compressed air is then used to run an air motor to assist the electric motor to drive the compressor in the first place. And then the cold, decompressed air is used to create industrial refrigeration effects. With Huston's invention, we have an industrial process that demonstrates that when air is compressed and the heat is extracted first, most of the pressure rise is still available to do additional work. This is what Tesla expected to find. The total efficiency of the system is significantly above that predicted by thermodynamic conversion rates. When Huston and his uncle tried to bring the system to market, they were told it would put too many people out of work, especially in the fuels trades. So this, I've just turned the patent diagram sideways here, and I just want to show you here. This is the electric motor driving the system. This is the compressor system that compresses the air. This is the heat exchanger that takes the heat out. Then the compressed air comes out of here, comes back down through the air motor, which is on a common shaft. So the air motor then expands the air that comes out after the heat's taken out, and the mechanical energy produced here relieves the motor of some of its load for running the compressor in the first place, and then the decompressed air is used to produce industrial refrigeration. So when you use both the heat gain and the refrigeration gain and the recovered mechanical energy, the efficiency of this is very high. How much is high? I'll show you in another patent where they show the graph coming up. So this is a simplified drawing of John Huston's invention, which I call the regenerative air-based heat pump. There are no special refrigerants in this. There is no phase change in this. This is just compressing air, taking the heat out, decompressing the air, retrieving the mechanical energy that's running the compressor, and using the industrial uses for the refrigeration as well. So you can see the cycle here. We bring in ambient temperature air, we compress it, that densifies the heat. The heat is taken out here for use through a heat exchanger. That lowers the temperature here. Then when we decompress it, we get some of the work back that helps support the motor or relieves the motor of its load. And then this comes out and it's colder than the ambient now. Then heat from the ambient can warm that up, and then it vents cool air. Fast forward to 1975, we have the work of Dr. Thomas Edwards. This image shows an article from the February 1975 issue of Popular Science magazine. It describes the latest tests on an air-only cooling system for automobiles. The system consists of a two-sided rotary vane motor compressor unit and some radiators. The original article had all temperatures listed in degrees Fahrenheit and pressures listed in pounds per square inch. I have converted these values for metric equivalents for today's presentation. The name ROVAC comes from combining the words for rotary vane air conditioner, just so you know what that word means. So basically what we have is that the ambient air comes in here. He lists ambient air at 24 degrees, which is a little warm for ambient in most places, but he was in Florida. So that was a little low for that. So all these tests were run in Florida. And so 24-degree air comes in, and he has this wonderful rotary vane, double-sided rotary vane device where the vanes go in and out. And they're actually riding on this inner cam here. And so they don't actually touch the edge. There's a very, very, very tight clearance there. So the friction, and all these things are running on rollers in here. So he's got the friction just down to just very, very low levels. This is a very, very fascinating thing. So this side then compresses the air, and the air comes out here at 140 degrees Celsius, comes into the first radiator, and basically here he's just got a fan on and he's throwing all this heat away because what he's trying to do is build an air conditioner for an automobile. So he's just throwing the heat away just to get rid of it and to lower the net heat in his compressed air. But even after he drops 95 degrees Celsius out of this air, he's only lost 3% of the pressure. He's still got, so it comes out here at basically 2.1 bars, and by the time he dumps the heat, it's down to 2.05 bars. And this is exactly what Tesla was talking about when he said there was an error in Joule's calculations about how much energy is really available in compressed air. So then he decompresses the air, and then it comes out here, and it's down to something crazy, minus 34 Celsius. And that's definitely enough to cool your car. Now, Edwards was issued 8 patents on this system with a wide variety of different features in the rotary vane device and in other things. But the reason we never got one of these things in our cars is that they never were able to take full advantage of the refrigeration side because the moisture in the air was freezing the whole thing up. And this was one of the problems that he ran into because he was doing the experiments in Florida. Okay, 100% humidity will do that to you. They were never able to solve the humidity problems, how to get the humidity out of the system before. You can see in the earlier image here, he's showing a heat bypass here to actually warm up, because the cold side was actually too cold. Everybody's got problems, right? So, but it wasn't helpful because the freezing was happening before then. So this system demonstrated a number of extremely important features for, again, what I call a regenerative air-based heat pump. But in the end, the system was abandoned as an automobile air conditioner. The inventor was so focused on one specific application that he didn't see any other possible uses. It's fascinating. So here's the answer to your question. How much? Well, Thomas Edwards was able to recover 85% of the mechanical energy. Okay? So what that means is that now we have a heat pump system that if you put 100 units of mechanical energy into the compressor, you not only can produce essentially a continuous volume of 140 degrees Celsius air through a heat exchanger. You can recover 85 units of that mechanical energy so that the electric motor or whatever is driving that only has to actually put in 15. And you also end up with this extremely refrigerated side at minus 34 Celsius. So if you look at all of these benefits simultaneously, you can see that this is enormously more efficient than the kinds of heat pumps we use today. It also demonstrates that the temperature and pressure of a flow of air are much less dependent on each other than they would be in an enclosed volume. This is another very interesting little detail that both Houston and Edwards independently discovered. Houston's patents were of such an early version that no listings were made for prior art or anything like that, but Houston's patents were not referenced in Edwards' patents, which suggests that he didn't know about them. He rediscovered all of these things independently. So using the data generated from the ROVAC system, we can start to piece together an understanding of Tesla's ambient temperature heat engine. First thing I'd like to do to give you a better idea of just how much mechanical energy can be recovered in this situation. And to do that, I'd like to convert the functions of the rotary vane device back to pistons and cylinders so we can more easily compare the work in and work recovered cycles of the machine. So here, what we have here is, this is obviously a simple compressor arrangement. And this represents a 360-degree illustration of the rotation of the crankshaft, okay? And so at top dead center here, this is the compressor side. So what we're going to do is at the top, when the piston is right at the top, we're going to open our intake valve here and swing around 180 degrees and close the intake valve, and that fills the cylinder with ambient temperature and ambient pressure air. Then we're going to go 90 degrees, and we're going to compress that by moving the piston halfway up, which is going to approximately double the pressure, which is all we need to do. Then we're going to open the exhaust valve and deliver air at basically 2 atmospheres to the next heat exchanger. So that shows you the basic cycle of the compressor. The piston, an identical piston is used as the decompression cycle. And again, at the top dead center, what happens is we open the intake valve and we go 90 degrees at full pressure from the system, delivering our 2.05 atmospheres of pressure. And so this first 90 degrees is under full pressure. Then we close the intake valve and we let the air decompress for the next 90 degrees. And that lowers the temperature and brings the pressure back down to 1 atmosphere, at which time we open the exhaust valve and we run 180 degrees around, bringing the piston back to the top and venting the air at atmospheric pressure and at minus 34 degrees Celsius. So you can see the decompression stroke is a mirror image of the compression stroke. When these two devices are mechanically connected, the losses in the system are simply the 3% drop in pressure between the input and the output and the frictional losses of both devices. As the Edwards patent suggests, this means that we only need to replace the losses, or 15% of the operational energy needed to produce and maintain the temperature differential at the heat exchangers. Does everybody understand this? Luckily, this isn't rocket science. This is really simple stuff. So this diagram simply puts this back into a simple form. I'm showing the heat cycle, and the only thing that this diagram doesn't do is it doesn't show you that the compressor and the decompressor are mechanically connected, rotating one for one. So here again is a representation of the regenerative air-based heat pump using piston compressor and decompressor components. The operational data from the working models of Thomas Edwards Rovac system are superimposed on the diagram. So this actually does fulfill Tesla's first requirement for a self-acting engine. With this system, we can not only establish and maintain an artificial cold spot in a very economical fashion, we also get the added benefit of establishing and maintaining an artificial hot spot at no extra cost. So let's now look at the problem of finding a high-efficiency heat engine. So standard model for efficiency, everybody knows this. Total energy out divided by total energy in, always less than 100%. Okay? This idea is based on the first law of thermodynamics, which states energy can be converted from one form to another, but it is neither created nor destroyed. So nature can convert these forms of energy with 100% efficiency, but our machines always introduce imperfections in these processes, and therefore the output is always less than the input. So there can be loss-free conversions, but no loss-free machines. So, heat engine efficiency is notoriously low. Everybody knows the efficiency of the automobile engine, 23, 24%, rest goes out the tailpipe, right? Okay. So here we have just a simple thing. We've got fuel running a gas turbine, and in this example, it's just turning an AC generator, okay? And if we can get 30% mechanical energy production out of a gas turbine engine, then we're doing really well. And that means that the rest of the energy from the burning fuel is coming out as what we'll just call 70% heat energy. So your automobile's rated about 23% in converting energy content of the fuel into mechanical energy to move the car. Tesla knew he could never get a machine to run on atmospheric heat if he was constantly throwing away 75% of the energy. So, what can we do? Well, we can raise the efficiency of the system by reusing some of that wasted heat. This is typically what's called cogeneration. It's used in a lot of industries. So while we can't make the gas turbine more efficient, we can recapture and reuse the waste heat to boil water and run a steam turbine to produce more electric output. So if the boiler and steam turbine are also 30% efficient, which is, I'm being very generous there, then we can recapture another 21% of the energy content of our fuel without burning any more fuel, raising the mechanical energy production from 30% to 51% and lowering the waste heat loss from 70% down to 49%. Further gains could be had if more stages of heat recapture and reuse were added. Anybody got any problems with this? This is easy stuff. Here's another example of how to increase the efficiency of a system. Let's look at a typical tabletop distiller as our basic model. What we have here is, this is standard stuff from, at least 10 years ago. I don't know if they're doing anything better these days, but water is placed in a sealed boiler. Electricity is used as a heating element to boil the water and make steam, okay? Then more electricity is used to run a cooling fan here and cool the steam so it condenses and the distilled water comes out here, and which is lovely, which is our preferred output, of course, and all the energy is used once and then thrown away. Standard stuff. So here's a more interesting idea. This is called a regenerative steam distiller. Cold water is held in a container over here at the exact level of where you're going to boil it over here with a float valve. So then the water comes through here, goes through a heat exchanger, and comes up to the heating element here. The heating element adds all the heat necessary to boil the water, but we know that that when the steam comes around, it's pretty hot, and it starts its condensation route back here. So we use the cold water to condense the steam down through here, and we transfer as much heat from the steam itself back to the cold water that's coming in to be boiled next as we possibly can. And we can keep using the same heat over and over and over and over and over and over and over in this loop to constantly make more steam and make more water. In this situation, we can take advantage of the fact that the heat of vaporization of water is exactly equal to the heat of the condensation of water that can be recaptured. This fact is straight out of the chemistry books. This is what I was saying before. Nature allows for 100% conversions. Okay? You get exactly the same amount of energy out when you condense water as you do as when you boil it. Both of those things are absolutely the same number of calories as in the book. The heat content needed to warm up the water and cool down the water is also the same. So once the system is up to operating temperatures, the only heat required to keep the system working is to make up the losses in the heat from imperfections in the insulation and the difference in the temperatures between the incoming water and the water that's entering the distilled water tank. So that's all you have to do is make up those differences, and that keeps the full loop going. All other heat is recycled repeatedly. In actual practice, this can lower the cost of producing distilled water by 90%. So, the idea that the energy used by a system or process is equal to the energy lost to entropy by that system or process is a matter of engineering. It is not a matter of natural law. It doesn't happen all the time. It doesn't have to happen. It can be delayed. Energy can be recovered and used again and again and again and again and again, as long as that's how you've designed the system. So let's look at our efficiency model again. Typical thermodynamic efficiency of less than 100%, or a closed system with a COP of less than 1. And this is typical what we have, our pitiful user input here. goes into whatever machine or process this is. There's always going to be some losses, whether it's friction or loss of, imperfections of insulation or whatever it is, I squared R, whatever. And then our preferred output, which is always going to be less than what we put in. That's the simple model. This is the classic energy efficiency model that most commercial products are designed to use. So our second model here, this is the typical heat pump efficiency, open system with up to a COP of 3. We have our user input. This is what we have to put in to our little heating element there. And this is the environmental input. This is for like a standard heat pump. So this is the heat we're taking out of the refrigerator box. Okay, this is the energy we buy from the utility to run the compressor. Okay, these two things come together, and our preferred output is how cold the refrigerator stays. That's wonderful. Out comes more heat. Everybody knows a refrigerator puts out heat into the kitchen, and our losses, of course, are the same. Friction in the compressor, and so on and so on, and and also. Heat getting back into the refrigerator through the very, very, very thin walls that are 4 times thinner now than they were 40 years ago. And I wonder if there's a reason for that too, but we won't go into that. So this is the energy efficiency model that covers appliances such as refrigerators, air conditioners, and other heat pumps, where energy from the environment can be harnessed along with user inputs to produce larger useful outputs, as well as returning some energy to the environment. Okay. So here's a modern regenerative system with open system with a COP greater than 5. Now what we realize is that we have an environmental input, we have the user input, we have our preferred output, and we have the same losses. But now all of a sudden this energy that was returned to the environment here, now we can just we can tap that and return it and put it back in the system. This is what we saw with the regenerative steam distiller. Now all of a sudden we're starting to see that energy can not only be rejected by a system, but it can be recovered and reused. So not only aluminum cans can be recycled, energy can be recycled. After all, it's you can't create it or destroy it. Why buy it, use it once, and throw it away? I mean, if it can't be destroyed, let's use it. Okay. So now that we know a little bit about how to raise the efficiency of a system, let's look at the Stirling engine. Now we know that I'm showing an alpha configuration here. How many you know a little bit about Stirling engines? You've certainly heard about Stirling engines. It's a very simple device. It produces mechanical energy simply by creating a hot zone and a cold zone and a special cycle which allows a working gas in here. There's no valves or anything else. There's a working fluid in here which is a gas. And by using the pistons to cover up or expose the heating elements and the cooling elements, you can force the gas to either expand or contract and create a work cycle out of it as the heat moves from the hot side and out the cold side. Okay? This type of engine was developed in the 1830s, right about the same time the first heat pumps were being demonstrated. And it was the first serious alternative to the steam engine. Its primary benefit was the production of mechanical energy from heat without the danger of a boiler and a pressurized steam system. These engines are much simpler than the more popular internal combustion engine used today, and they can easily attain similar efficiencies of between 20 and 25% when properly engineered features are included. So let's combine all these ideas and see what we get. Anybody know where I'm going with this? Okay. where I'm going with this is to run a Stirling engine from a combined heat pump cycle. Okay? So here's the compressor, and here's the decompressor, and here's the crankshaft of the motor. I'm showing this diagram shows primarily what's going on with the heat in the system. So if I take ambient heat in here, this big radiator is used to register the air and make sure that it comes out at 20 or at ambient temperature all the time. If we don't stabilize the temperature right here, then the whole thing can run away in one direction or the other. So, but we end up with a machine that has 4 pistons and an external radiator. It looks a lot like an automobile engine from if you don't look at it too close, except it doesn't have any valves and it doesn't have any ignition system, and it doesn't have about 90% of the parts. Okay, so basically the cycle is that the high temperature is produced here, and the more heat we extract here, the cooler this will be, and when we decompress, the colder this will be. And so the colder this will be, the more easily the heat will move through it and come back out into this system, warm this up, and the less we'll have to put in again to bring it back to here. So when these two systems are mated together, supported by a constant heat input from the environment, it should produce what is called a virtuous reinforcement cycle. We know that the heat pump can produce 174 degrees centigrade or Celsius temperature differential for the heat engine to operate on. And we know that for the system to become self-running, the engine only has to overcome its own friction and the low mechanical input requirement of the regenerative heat pump, which we already said was only 15% of what it takes to run this compressor. This seems tantalizingly possible, especially because all unused heat and mechanical energy are recycled in the system. So now we've got something where we're not just recycling heat, like in the steam distiller, or mechanical energy as in the regenerative heat pump. Now we're recycling both the heat and the mechanical energy. So here we have an advanced regenerative system with an open system with a COP greater than 10. We have our environmental input. This is the heat that we have to constantly replace in the system. We have the user input, which we are hoping is only a starter motor. We have to turn this thing for a while to get the temperature up to get the motor running. All forms of energy in the system, which are just heat and mechanical energy, are both recycled until they come out of the preferred outputs, which is the shaft of the Stirling engine and or the cool air coming out of the radiator. All other heat and mechanical energy is recycled in the system to go through the system over and over again until they come out either here or at the radiator. Now, this is not where Tesla expected to find the solution to his self-acting engine, but this is where one iteration of his idea becomes accessible. Tesla expected the machine to operate entirely on an input of environmental heat while producing mechanical energy and refrigerated air as a byproduct. My proposed design accomplishes this, not with high-efficiency components, but by using high-efficiency energy management methods. So basically, we can look a little bit at our efficiency models again. Here's the basic one. All of the components in this machine operate on this. In other words, there's losses in the compressors, there's losses in the expanders, there's losses in the Stirling engines. each component is operating at under 100%. However, the way the system works together and all the feedback mechanisms in it, the total energy output divided by the user energy input, which is our definition of COP, can be way over 100%. And by using environmental inputs and by recycling multiple forms of energy, it's possible that the user inputs can be reduced to zero, which gives us a self-running machine. Does everybody understand that idea?
Why is it not on the market?
Nobody showed me how to do this, okay? Nobody's been looking at this. These developments are historically important. Now, we can create a better future by using energy available from the environment. First and second laws of thermodynamics were important in their day, but do not represent valid limits for commercial products anymore. Heat pumps have been demonstrating COPs of 3 in our refrigerators and air conditioners for decades, and now they're being marketed in hot water heaters and clothes dryers too. Advanced regenerative systems that recycle both heat and mechanical energy repeatedly will usher in an era of machines with COPs greater than 10. Now, just for clarification, I want you to understand that there's 2 basic technologies here. The first one is the regenerative heat pump. And this goes back to Houston's patented designs and working models, and also Thomas Edwards' patented designs and working models. Both of those guys, 45 years apart, both discovered that if you just compress the air 2 to 1, you get a huge heat swing in the system, and it's all very simple to close the loop and recover up to 85% of the mechanical energy needed for the compression cycle in the first place. So this is not theoretical at all. This has been proven twice in industry. The fact that neither of these things were allowed on the market is a totally irrelevant point. Okay? The regenerative heat pump can be used for water distillation, water space heating, water heater or space heater, air conditioner, furnace, refrigerator or freezer, industrial dryer or dehumidifier. It can be used for extremely efficient heating of greenhouses and anything else that may require heat or cold or both. The regenerative heat engine, if we can take a heat engine and put it into a cycle like this and use it, then we can use the unlimited heat in the ambient air, which is replaced by the sun all the time, and create a reliable base load power from solar energy available anywhere on the globe. No atomic reactions, no nothing, okay? Just heat recovery from the atmospheric air can be used to produce mechanical energy in an extraordinarily efficient manner. These can be used for home power plants, which not only would give us electricity, but also direct heating and cooling, which are usually some of the biggest users of electricity. So we don't even have to produce as much electricity when we handle all of our heating needs directly. These things can be used for industrial power plants, transportation systems, and can be used on land, on or under the water, or in the air. One simple iteration would just be for a solar home. If you don't want to go all the way and build an engine out of this, you can create a regenerative heat pump that's just where the motor is driven by a solar panel. And all of a sudden, maybe for a 200-watt solar panel, I could run a hot water heater and my refrigerators and freezers in my home. Now, that's something a 200-watt solar panel won't do under normal circumstances. But with the gains of a regenerative heat pump, we can do it. All of a sudden, wow, This is helping us get off the grid because we're eliminating the need for certain types of energy by using environmental energy directly, the heat of the ambient air. We can also turn this into a very high-speed turbine arrangement where we have a turbine compressor, a turbine decompressor, and a turbine expander contractor engine, all of those turbines on the same shaft with heat exchangers around. We can turn this into a big engine. Bunch of turbines and a bunch of heat exchangers, and there it is. This is closer to what Tesla was expecting to be able to do. So some of the advantages of this technology is it's made from combining two well-known systems. About all the engineering that will ever need to be known about how a heat pump works and how a Stirling engine works are sitting in the books. I mean, have been for 1.5 centuries. Okay, there's no new science to discover or verify. I mean, we're not cracking neutrinos out of oranges or something. I don't know. Runs on known and inexhaustible and recognized energy source, solar heat. Okay, this isn't. There's no mysteries. So it allows solar energy to be harnessed 24 hours a day, 7 days a week, 365 days a year. And no location is any better than any other. So this allows, so there's no special materials needed. You can build these things out of aluminum and copper and steel and graphite. I mean, there's no explosions or anything. You can use graphite lubricants and all kinds of, this is cakewalk. It doesn't, there's no pollution. It runs quietly. There's no exhaust. There's no valves. There's no complications. These are very, very simple machines. They can be developed and deployed rapidly, could help lift billions of people out of poverty, and lower the carbon footprint dramatically. So the disadvantages of this technology are that all the building blocks are in the public domain, and this would discourage venture capitalists from being involved because they want to make sure they can control the IP and everything, and that's going to be more difficult. I mean, after millions of dollars, we might be able to come up with some, new IP, but not from a theoretical operation of the machine. You may be able to come up with, a better screwdriver or something to fix it, but that's about it. It encourages decentralization of power production, and there may be some pushback on that in the greater economy. It encourages local production of clean water. And of course, there's probably people out there who don't want us to have clean water. And encourages local production of food, encourages practical solutions that are possible, unmasks the lies supporting scarcity theory, and I call it scarcity theory because really this whole field of energy developments is about abundance availability. And so this sort of thing is, it busts the lie pretty dramatically. And it changes the value of money, honesty, and sharing, which of course there will definitely be some pushback on that. So 120 years ago, Tesla said, it's a mere matter of time when men will succeed in attaching their machinery to the very wheelwork of nature. In my estimation, that time is very close now. Humanity is approaching an epical decision. The technology of abundance is arriving. The planet is only in peril if humans keep fighting over short-term profit and long-term advantage over each other. Society must refocus its priorities toward world peace, genuine ethical behavior, and the implementation of completely sustainable technologies. So if governments, financial institutions, business leaders, religious leaders, and the media will not work toward these goals, then the rest of us, we have to lead the way. If we don't give the younger generation something positive to believe in, something that can electrify their hope, that the world can become a better place and that society can solve its problems. They will be recruited to tear down what they clearly see as the forces that are stealing their future. We see this already showing up on the television screen. We know this trend is in tow. If we don't combat this, they will be recruited to do something that is against what they see as bad. We need to recruit them to be for something that is good. And it is up to us, because right now they're being recruited. Near the end of his life, Tesla said, "The desire that guides me in all I do is the desire to harness the forces of nature to the service of mankind." This is the grand manifesto of a true natural philosopher. Tesla was totally honest, and his motives were pure. He believed that the benefits of scientific discovery should accrue to the whole of society for the genuine support of real human needs. He also believed that the ambient air heat engine was the best way to harness solar energy and the ideal method to power civilization indefinitely into the future. Humanity needs to know if this arrangement of stuff self-runs. In spite of the simplicity of this idea, the mathematical modeling required to verify its operational efficiency is actually fairly complex. What is needed is to put this conceptual model into a full physics 3D simulation software program and fully explore its characteristics. Such a project will require a true angel investor, someone who does not need to profit financially and who genuinely wishes to contribute to the possibility of a better future. But we're running out of time. Our fragile home is currently more polluted than at any time in its history, and the humans are definitely to blame. In a world with increasing divisiveness among peoples, rise of remedy-resistant diseases, malnutrition on all continents, increasing extreme weather events, and political dysfunction in most of the major democracies, the Spirit is asking us to contribute all of the wisdom, compassion, sanity, honesty, integrity, and loyalty to truth that we possibly can. It is also asking us to gift to the whole of humanity the technology of abundance. We are all called to act, to put need before greed, wisdom before sound bites, compassion before judgment, sharing before hoarding, gratitude before blaming, respect before understanding, and honesty before money. Right now, the enemy is us, if we don't all reach out for the highest good of all. Unlimited access to solar energy is here. It's time for us to do something about it. Thank you.
And that is Dr. Peter Lindemann.